Welcome to the New Calculus channel. My name is John Gabriel. Today I'm going to discuss the so-called postulates or axioms that were written down by Euclid. And I'm going to reveal some information which I believe most academics throughout the ages have never realized since the time of Euclid. And what you're looking at right now is a copy of the elements in both the original Greek on the left-hand side and the translation by Sir Thomas Heath on the right-hand side. Well, first of all, if you look at the ancient Greek word that is translated into postulates, it really doesn't mean postulates. And that word that you see here is pronounced etimata, okay? And what that means is claims or requirements. So a claim that somebody makes or a requirement that somebody needs is not a postulate. So a postulate is a complete mistranslation of the original Greek word. Incidentally, that word is not used very much in the modern Greek. So, and of course, there's another word that goes along with this word here. If we look at the first definition, eutisto, it's an ancient Greek word which doesn't really have a modern equivalent. So, this very first requirement or claim states Itisto apopandos simio epi pan simion ephian gramin agayun. Now what that means is that you can you can produce a straight line from any point to any other point. So it doesn't actually even say anything about draw, and this is not a correct translation. You could argue that they are the same thing, but they're not really the same thing. And let me explain to you why it's wrong to say draw as opposed to produce. Okay? Well, if you have two locations and what you see there, those two little dots I've made, or points, they're not really points. They're just visualizations of a location in a plane. Consider this white space here a plane, a flat plane. So they're not really points. They're just visualizations. You can't construct these abstract concepts tangibly. So all you can do when you try to explain things to one another or to academics is to try to visualize what they mean. What this means is that we're referring to this location in the plane. So that's not a point, that's just a little blob, alright? Now, I was talking about the word draw and produce. Now, you cannot do that. You cannot do this here. Okay, that's not exactly a straight line, but okay, now it is. You cannot do this and then say that this object here is a line. It's not a line. It's a visualization of a line. But what is a line? Well, let's go and check how Euclid defined a line, and we'll know what the definition of line means. So if you just go back to the previous part in definitions, it says, and the line is a length without breadth. And of course in the original Greek it's grami ve mikos aplates. Okay? So really a line is a length without breadth. It cannot be anything like this. Okay? This is entirely wrong. It doesn't matter how thin you make that line, it's not a line. And this here is not a rectangle, and this here is not a circle. You might be dropping your jaw now and frowning, but no, I'm telling you the truth. This is not a rectangle, this is not a line, this is not a circle, this is not a triangle. So what are they? Well, They're visualizations of these abstract geometric objects. You see, these are paths. All these objects here consist of paths, alright, or routes from one point to another, or a set of points. So when you think of a line, it's really the shortest path between 2 points. Okay, you can have many points, many paths between 2 points. You can have this path, you can have that path, you can have this path, you can have that path, and many of these paths here may be equal to each other in length, but you can only have one path, like that. Well, let me redo it. You can only have one path which is the shortest length between the 2 points. Okay, so this length, this path here, is called a straight line because it is the shortest. It is the shortest distance or length. Right? Does that make sense? So now, what is a straight line according to Euclid? Well, let's go back and check. So definition 4 tells us a straight line is any one which lies evenly with points on itself. That's kind of a very obscure or vague definition, and of course even the ancient Greek is kind of hard to make too much sense of. It says ethia grammi estin itis ex isu tis eaftis simios kita. Now really that's a mouthful, and even modern Greeks don't really understand it properly. But what it really means is this: a straight line can't be placed evenly on any other line unless it is a straight line also. But other lines have equal length but cannot lie evenly on each other. So what am I talking about there? Well, if you have 2 points here, you have this point. Let's just change the color so you can see what's going on. And another point there, like that. Okay. Now, if you have, let's say, a line like that, and another one which goes like that, and these two presumably are the same distance. Now, you cannot take this line here, this line, and place it evenly over this line here, right? It's just not possible, even though they're of the same length. So the only way you can do this is if you have a straight line, right? And a straight line doesn't correspond to any other path from this point to this point which has the same length, and hence that path is a line because it has the shortest distance. Does that make sense? So if we go back to the postulates and look again at the very first one, over here it says let it have been postulated to draw a straight line from any point to any point. There's really nothing to prove there anymore, is there? Because we've defined what is a line, and this isn't a postulate. It's just a statement or a claim which was made by Euclid, and it's a very valid claim because of what I've just explained to you. What about the word axiom? Where does that come from? Well, get ready for this late blockbuster newsflash. The word axiom appears nowhere in Euclid's Elements. In fact, it didn't even appear until several hundred years later. Okay, so the word axiom was not found anywhere in the Elements. Then of course we have the common notions. Now, if you look at the common notions, these also do not require proof. They're actually straightforward. The ancient Greek here says kine N-O-N. Okay, that really means common meanings. Common meanings. And of course in modern Greek they don't really say enia. They just say enias or kimi enias. So it doesn't have the alpha iota. It has an omicron iota in the modern Greek. But that aside, these are the common notions, and of course they make perfect sense because there is nothing here that needs to be true. If something is equal to the same thing, then it must be equal to the other thing that's equal to the same thing, yes? And so we go through all these common notions which are not postulates or axioms or anything like that. So just before I finish off here, the translation here says that the imperative itisto could be translated as let it be postulated. That's false. It can't be translated as let it be postulated or even let it stand as postulated. Okay, so I don't know how Heath arrived at this understanding here, but it's definitely not correct. And just to finalize on this particular topic, the word postulates is a bad choice. It should rather have been something like claims. Let me just write this down here. Claims or requirements, or some other synonym, but definitely not axioms. Okay, they're not axioms. But what is an axiom really? Well, an axiom is really something that has worth. Okay, and there's also a Greek word for axiom. In fact, several versions of it. Axia, axios is the male form. Axia is also the female form. Axio is the neuter. So there are several forms of the word axiom, but in mathematics, a definition graduates to an axiom after it has been vetted, right? So the reason Euclid's elements are still around today is that they have withstood the test of time, and they're not axioms by any stretch of the imagination. When Euclid wrote down the elements, they were not thought of as axioms, but rather claims or requirements. So just to summarize, all the geometric objects, such as lines, squares, triangles, all these here deal with the concept of shortest distance. For example, you could say that if you have 3 points like that, that is a symptom of a triangle, right? So 3 points are a symptom of a triangle. 2 points are a symptom of a straight line. And 4 points are a symptom of a rectangle. You don't even need to draw lines in between the points, because lines, those are not lines. This here is not a line. Neither is that. This is not a circle. These are just visualizations. Okay, visualizations. That's all they are. These objects here are all abstract. And so when you think of a triangle, it's the shortest path connecting 3 points. That's a triangle. That's the exact definition. This here is just a visualization or a tangible instantiation of the concept of triangle, right? Just as a line is a visualization of the instantiation of the shortest distance between 2 points. So that's all kind of hard to explain and can get one into a real twist as far as reasoning and logic goes if it's not done properly. But the very first axiom, or not axiom, the very first requirement or claim is that a straight line can be drawn from any point to any other point. It's not an axiom, it's actually provable, as I've shown you over here. It's a definition, it's the way a straight line is defined. Okay, so a straight line doesn't correspond to, in distance, it doesn't correspond to any other of the paths between two given points. And as I said, you cannot take equal paths like this anywhere else and overlay them exactly on another equal path. The only time you can do that so that the points lie evenly is with a straight line. Okay, this has been a presentation on the first postulate of Euclid, and my name is John Gabriel. This is the New Calculus channel. I hope you'll join me again next time for another interesting video.